Well, good day. And today's topic is 46 domain specific IoT, health and lifestyle in applications in IoT. So, the domain specific IoT, like health and lifestyle IoT, it's a two domains of health and lifestyle IoT. This domain is broadly split into two categories with different stakes and requirements. One is clinical healthcare, IOMT, and regulated high stakes focused on diagnosis, treatment, and monitoring of medical conditions. Examples: remote patient monitoring, smart insulin pumps, connected pacemakers, and CSE focus extreme reliability, data integrity, and security life critical systems. And next one is the personal lifestyle and wellness, consumer grade focused on wellness, fitness, and preventive health. Examples: fitness bands, smart scales, sleep trackers, CSC focus, user engagement, data visualization, and long term battery life. The IoT architecture in health and lifestyle. This architecture highlights the specific components and challenges in the sensitive domains, like, say, for example, sensing and perception layers. It is biosensors and wearables. Uh, those are that we can relate, and health and lifestyle applications and examples like clinical sensors, ECG, EKG, blood glucose, blood pressure, pulse oximeter, metry, and lifestyle sensors are like accelerometer, gyroscope, GPS, heart rate, uh, galvanic skin response, actuators, insulin pump, dispensers, and haptic feedback for alerts. And network communication layers are like short and long range protocols, and in health and lifestyle applications like on-body or pan, Bluetooth low energy BLE, the domain the dominant standard for connecting wearable to phones. In-home or LAN Wi-Fi for stationary devices, smart scales, bed sensors, WAN cellulars, 4G, 5G for fall detection pendants that work anywhere. And data processing layer, edge versus cloud computing, edge on device phone, immediate anomaly detection. Example: fall detection, irregular heartbeat alert, reduces latency and power consumption. Cloud computing aggregates long-term data for trend analysis, population health insights, and advanced ML model training. And application and interface layer, software and analytics, clinical dashboards for doctors to monitor patients, integrated with electronic health records, EHR, consumer apps, gamified, and fitness goals, sleep score dashboards. Example: Fitbit, Apple Health, alerts and notifications to the user, caregiver, or emergency services. And security and privacy layer, property concern, critical encryption in transit at rest, strict user authentication, and compliance with regulations like HIPAA, Health Insurance Portability and Accountability Act, and GDPR. Health data is highly sensitive. Practical use cases and system designs like, for example, use case one, remote patient monitoring are aimed for chronic diseases. In this, the problem is managing chronic conditions like congestive heart failure, CHF, outside the hospital to prevent ready, readmissions. And IOMT solutions like sensing, communication, processing, and one is processing edge and processing cloud and applications. Like IOMT solutions, in the first one is sensing, where a wearable patch measures ECG, heart rate, and respiratory rate. A smart scale measures weight daily. This is a primary activity happens in this, the sensing part. Next one is communication part. The BLE sends data to a patient's smartphone, which uses Wi-Fi cellular to transmit it to the cloud platform. Processing edge. The smartphone app checks for sudden critical anomalies, example, arterial fibrillations. And processing cloud. ML models analyze trends, a gradual weight gain, a key indicator of fluid tension in CHF, triggers an alert before the patient feels acute symptoms. Applications like the care team's dashboard flags the patient for a proactive telehealth intervention. Use case 2, personal Fitbit and sleep tracking, like the problems of users want quantified data about their activity and sleep quality to improve wellness. IoT solution sensing a fitness band uses an accelerometer and gyroscope to count steps and detect movement. An optical heart rate sensor and SpO2 sensor monitors sleep stages. Communications really syncs data periodically with the user's phone, and processing edge or cloud, sophisticated algorithms on the phone or cloud classifies like activity running versus what. Calculate calories and analyze sleep patterns like deep REM. Application, the user sees a daily readiness score or sleep score with recommendation to recovery. improve recovery. Key technical challenge for CAC students, power consumption and battery life. Wearables must be small and lightweight, demanding ultra-low power design, sensors, processors, and BLE, data accuracy and sensor fusion. Consumer sensor data can be noisy. Reliability is improved by sensor fusion, example combining accelerometer and gyroscope data for more accurate activity evaluation. And interoperability and standards, a major hurdle is getting data from different devices. Example, a Garmin watch, a Withings scale, and a glucose meter into a single cohesive platform. Standards like FHIR, fast healthcare interoperability resources, are emerging to solve this. Security and privacy, this is non-negotiable. A breach of health data is catastrophic. Furthermore, data must be anonymized for research to protect patient identity. Regulatory compliance, building clinical devices requires understanding and adhering to medical device regulations, example FDA in the US, which impact the entire software development lifecycle. In class activity, design a post-surgery recovery monitor scenario. A patient is discharged after knee surgery. The care team wants to monitor their mobility and pain levels at home to ensure a safe recovery and flag potential complications like infection or blood clots. Task in groups, students must design an IoT system for this purpose. Deliverable, a brief architectural diagram and explanation covering and sensing what sensors would you use and how. Example, a wearable on the ankle to measure range of motion and gait speed. A smartphone app for daily pain level surveys. Communication, how is data transmitted? Example, BLE from wearable to phone, then Wi-Fi to the cloud. Processing, what simple rule or algorithm would trigger an alert? Example, if gate speed decreases by greater than 30% for two uh, consecutive days and self-reported pain increases, then send alerts. Interface, who gets the alert and how. Example, a notification on the case manager's dashboard. Ethical considerations and discussion points. Data ownership, who owns the health data, the patient, the device company, or the hospital. Algorithmic bias, if an ML model is trained on non-diverse data set, could it lead to misdiagnosis for underrepresented groups? The nudge effect, something like how responsible or developers for the psychological impact of constant health scoring and notification. Insurance and discrimination, could this data be used by insurers to deny coverage or increase premiums? Further reading or project ideas, like you can go for reading like role of Bluetooth low energy BLE in IoT and HIPAA security rule technical safeguards, and a project idea like hardware use and Arduino or Raspberry Pi Pico with the BLE module and an accelerometer. Software tasks are like program the device to act as a simple fall detector when a fall like motion is detected. A specific accelerometer signature, it sends a BLE alert to the companion phone app. Learning outcomes are like once you complete this, you'll be in a better understanding about and experience about sensor data acquisition, BLE communications, designing for a critical real world health applications. You are ready for that. Thank you. Bye.